Hello, everyone. Welcome to our first online lesson for however long this is going to go on. In this lesson, we're going to talk a little bit about planes. Okay, if you're in the period 2 class, we did do this lesson on the Friday before March break, but the period 1 class, you were one lesson behind the period 2 class because of the Ash Wednesday service. So we're just going to go over that lesson I guess again for the period 2 class, and it'll be fresh for the period 1 class. So I'm also going to do a quick little review of what we covered in this third block so far right now. Okay, because just the basic idea is we're switching from vectors to equations of lines and planes. Okay, and starting with lines, okay, what we basically saw so far is that for lines, okay, kind of the scalar form of the equation was the equation that you've already done in the past. Okay, so the scalar form was like y equals mx plus b. Okay, or if you rearrange it, you have what we call the standard form in grade 9, ax plus by plus c equals 0. Okay, but then we switched over to vectors. So the vector form of the equation of a line, okay, looks something like my line. Okay, so any point or position vector on my line is given by some initial point, x naught, y naught. Okay, and actually let's bulk that up to 3D right now. Okay, in 3D, this was x naught, y naught, z naught, okay, plus t, m1, m2, m3. Okay, and the reason we went to vector form is really for that 3D case. Okay, but the idea being, this is my line somewhere in 3 space. Okay, and if I have my little axis down here, so like x, y, and z, something like that. The idea is to get up to the line, right? I start with the direction vector. Okay, sorry, not a direction vector, that's my position vector. Okay, that gets me onto the line. Okay, then the second part, right, my direction vector, okay, tells me which way the line is going. Those are the 2 pieces of information I need to create the equation of a line, right? I'm trying to get on the line, so that's this part here. And once I'm on the line, I'd like to know which way it's going. So that's the second part here, right? This is my position vector. Okay, and this is my direction. Okay. In the previous lesson to this one, we got into equations of planes. Okay, so a plane is like a flat surface in 3D space. So if you imagine taking a piece of paper and kind of pulling it into the air, it's something like that. Okay, in the previous lesson, we talked about the vector form. So to create this lovely sheet in space, again, if I have my axes down here, x, y, z, something like that, okay, right, how do I create the equation of a plane? Well, first I want to get on the plane, so I start with a position vector that puts me onto that plane. Okay, and then, well, I need some kind of direction here, so I'll pick one direction on the plane, but one direction is not enough because that would just give me a line. Okay, so I need some second direction as well, and that will define a surface in 3-dimensional space. Okay, so the vector equation of a plane, I used pi. Okay, so any point on this plane can be given by a combination of my initial position, right? So a point on the plane, x naught, y naught, z naught, okay, plus a first direction vector, t, and then we had a1, a2, a3, okay, plus a second direction vector, plus s, b1, b2, b3. And we had other forms. We had parametric and for planes. We did symmetric for lines, but those are in the other notes. Okay, those are the basic ideas we've covered so far, right? Is that for a line, you need a position vector and a direction. Okay, and for a plane, you need a position vector and two directions to map out the surface. Okay, we also briefly mentioned in a previous lesson that another way you can set up the equation of a plane, right? The scalar form looks like ax plus by plus cz is equal to, oops, b plus d is equal to 0. It kind of looks like the center form of the line, but with three variables because now we're in 3D and that gives us a plane. Okay, so for the first part of this next note, that's going to explain where that comes from. Okay. So why that equation works, okay, or where it comes from. So I've got my plane, okay, so I know that I have some point P. Okay. We mentioned the idea of a normal vector a little while ago. So a normal vector to a plane just means it's perpendicular to the plane. Okay. And I'm going to imagine a vector I create on the plane. Okay, so pardon me, it's not P's not. Okay, so I can create any vector to some point on the plane if I know an initial point and I have a normal vector. Okay, so we're going to start with that. So given, and actually, I'm just going to make this a little faster here for you. So given our normal vector n, okay, so vector is perpendicular to the plane that passes through some point P naught. Okay, so I'm saying I have my vector and I know the point where it was. Okay, and some other general point P. Okay, so that's this right here. So my three different things: a normal vector, the point it passes through, and some other point P. Right, this is a general point. It could be anywhere. It could have been over here, and making the vector like that. Okay, well, it doesn't matter where P is. This new vector here is going to be perpendicular to the normal vector, right? Kind of, by definition of normal. Normal is perpendicular to everything on the plane, so any vector in the plane is perpendicular to that. Okay, so we note that the vector running from P naught to P is perpendicular to our normal vector. Okay, so we're going to use that fact to start generating our equation for the plane. Okay, so I know that n dot P naught P has to equal 0. Okay, so for normal, we'll use what will eventually appear in the equation. So we'll call that A, B, and C dotted with. Okay, how do I create the vector P naught P? Okay, well, P naught would have coordinates x naught, y naught, and z naught. Okay, P would have coordinates x, y, and z. Okay, and to do the vector that runs between them, right, I take my second thing, P, and subtract the first one. Okay, so my vector P naught P looks like x minus x naught, y minus y naught, and z minus z naught. Okay, and that has to be equal to 0. So now we're going to expand this part out. Okay, so right for dot product, I just take each coordinate, right, and multiply it by the same thing over here. So my first one, I'm going to get ax minus ax naught. Okay, for my next term, I've got b, so plus by minus by naught. Okay, and then for c, I multiply those together, so plus c z minus c z naught. Okay, and the entire thing is equal to 0. Okay, I'm now going to collect some things here. So we'll recognize the pieces we need. There's my ax, by, and cz. Okay, ax plus by plus cz. Okay, and then I have these three other pieces, right? This one, and this one. So minus ax naught minus by naught minus cz naught. Okay, so that mostly looks like our scalar equation. So now for the final little trick. This chunk right here, these are all things I was supposed to know. Okay, I knew my normal vector, A, B, C. Okay, this was the point on the plane that I knew, not the general point. So I know what those coordinates are. So this is not just going to be a number when I work it all out. Okay, so I'm just going to call that chunk D, okay, because it would be a number of some kind, okay? And that's what gives us our form of the equation. Ax plus by plus cz plus d, right, this constant from all those terms, is equal to 0. So that's where the scalar equation of a plane comes from. So now there's some examples of how to put together the scalar equation of a plane. So here's example 1. Determine the equation of a plane with a normal of 2, -2, 6, and decision point -1, 7, and 4. So this form looks like ax plus by plus c equals 0. I'll start filling in what I know. Oops, pardon me. That's not quite right, is it? That was for a line plus cz plus d equals 0. Okay. I start filling in my normal. So my a is 2, my b is -3, and my c is 6. Okay, so 2x minus 3y plus 6z plus d equals 0. The only thing I still need to figure out is what's that value of d. Okay, but because I know the point over here, there's my x, y, z right there. So I'll just fill those in, okay, and use that to figure out d. So 2 times -1 minus 3 times 7 plus 6 times 4 plus d equals 0. And let's do some calculations here. So let's just see here. This is going to be -2. And this is -21. And this is 24. So if I put all of those together, I'm going to get 1. So I have 1 plus d equals 0. And so d equals -1. So now that I found d, I can just write out my equation with all the different pieces in there. So my equation is going to be 2x minus 3y plus 6z minus 1 equals 0. And that is the equation of the plane. Okay. So in the previous lesson, we saw that, right, for the vector form, you need to have a point on the plane. That's your position vector in the two directions. For scalar form, you only need to know the scalar. Sorry, you only need to know the normal vector, and you need to know a point. So those two pieces of information will give the equation. Okay, example 2. Determine a scalar equation of a plane containing the points A, B, and C listed here. Okay, so this is very different because we don't have a normal vector. We have lots of points. So we'll do a little sketch here for a second. Just think about what's going on. Okay, so I have 3 points on my plane, A, B, and C, wherever those are. Okay, to create the scalar form, I need the normal and I need a point. Okay, I have lots of points. But for the normal, right, I need something perpendicular to the plane. So let's say if I use A as my reference for a second, right, I need a vector that's perpendicular to this. Okay, how can I get that? Well, because of all those points that I have, I could create some vectors in here. There's A to C, and there's A to B. Okay, and if I want to find something perpendicular to both, okay, we can use the cross product to figure that out. Okay, so those are going to be my steps here. I need to figure out those two vectors, so A to B and A to C. Okay. And then I'm going to do cross product to get my normal vector. Okay, so first for A to B, I have to subtract the coordinates. So I'm going to have 7, 6 take away -1 is 7, and 2 take away -2 is 4. Okay. And for A to C, let's see, I've got 5 take away -3, that's 8. -4 take away -1 is -3, and 1 take away -2 is 3. Now that I have my vectors, we're going to do the cross product. So I'll just kind of run that on the side here. That's 7, 7, 4, 7, 7, 4, 8, -3, 3, 8, -3, 3. See 21 plus 12, so that's 33. 32 take away 21 is 11. And 21, -21 take away 56 is -77. Okay, so my normal vector, by doing the cross product of these two vectors, is 33, 11, and -77. So now I have enough information to basically proceed like we did in example 1, right? So I'm going to start, I can fill in my normal, and then fill in a point and get my equation. But before I do that, and I know we talked about this before, I can make this a little bit easier on myself later, okay, if I simplify this vector, because I really just care about the direction of the normal vector. Okay, so I can use a scalar multiple, making numbers simpler. So this is similar to using 3, 1, and -7. Okay, that will make my life much easier in the calculations if I have the smaller numbers. Okay, so this is something to look out for. Okay, with a normal vector, right, you can do that. In fact, with any direction type vector, you can do that. You can't do it with position vectors because they're points, but you can with directions. Okay, so we'll pick this up now. So to get the equation of my plane, right, the form is ax plus by plus cz plus d is equal to 0. Okay, we figured out our normal was going to be 3 plus 1 minus 7. Okay, and then for a point, okay, I've got 3 different points up there. To make my life easier, I'll pick the one that's got all positives in it. So 4, 6, and 2. So 4, 6, 2, and that's equal to 0. Okay, and now I'll just solve that for d. So I've got 12 here, 6, and minus 14. So that comes to 4. Okay, so 4 plus d equals 0. D equals -4. So that means my equation is going to be 3x plus y minus 7z minus 4 is equal to 0. Okay, and if I recall correctly, from when I taught this on the Friday before the break with the period 2 class, we solved this a slightly different way because we ended up with negative, negative, positive in our initial normal. But it all, and I think we use a different point too, so it all comes out to the same thing in the end. Okay. Last example, determine the scalar equation of a plane that contains the line xyz equals 1 to 4 plus t 4, 1, 11, and it's perpendicular to this other line listed here. So think about what's going on here. We'll draw a little picture. Okay, here's my plane. Okay, it says it contains the first line. So L1 lies inside of this plane. Okay, that means that the point that I had there, 1, 2, 4, is on the plane. Okay, and the direction vector, 4, 11 is on the plane. Okay, my line is perpendicular to the second line. So we'll draw some other line like this. And I'm passing through here. Okay, with the new line, okay, I know my direction vector lies along this line. Okay, the point, I don't know if it's on the plane or not, because it could be down here. I don't really know about that point. So what do I need for the scalar equation of a plane? Well, I need to do a normal vector, something perpendicular to the plane. But I've got that, because this line is perpendicular to the plane. So this is going to be my normal vector. Okay, the other piece of information I need is a point on the plane. Okay, that's going to come from line 1, because I know this is inside the plane. And we're basically ready to go here. Okay, so ax plus by plus cz is equal to 0. Oh, I did it again. Plus d. Okay, and then we just start filling it in. So a is 2. So we'll do it all at once here. Okay, so a is 2, and my x coordinate is 1. B is 3, and my x coordinate is 2. C is -1, and my x coordinate is 4. Plus d is equal to 0. And we just work that around. So 2 plus 6 minus 4. That comes out to 4 again. So 4 plus d equals 0. D equals -4. Okay, so this equation is 2x plus 3y minus z minus 4 is equal to 0. Okay, so that's how you can create the scalar equation of a plane. Okay, so here is the practice work from your textbook, which starts on page 459. Okay, and see, a lot of that is just part A for a lot of those questions. Okay, so final thing, when I go to make the next video tomorrow evening, probably around 8:30 is when we'll start. So if you send me questions during the daytime, okay, I will answer some of those to take up homework, okay, before the start of the next lesson, or I'll do 2 separate videos, something like that. Okay, but this is your refresher on lines and planes and learning how to do scalar. So thanks for watching, and I hope to see some questions from you, and stay tuned for the next video.